Welcome back, and in this series of videos we're going to be looking at bond polarity, a short but very important topic. So bond polarity is a green topic and it's in the section under bonding. It's useful because it allows us to explain why some compounds are ionic and others are covalent. In diatomic molecules, you have a completely symmetrical electron cloud. So by a diatomic, we mean molecules where the two atoms are the same. So oxygen, nitrogen, chlorine, fluorine, and so on. These are examples of non-polar covalent bonds. The reason that they are non-polar is that they have a perfectly symmetrical electron cloud. So for example, hydrogen, you have an electron cloud that looks like this. Apologies, with your two nuclei, but the electron cloud around the two hydrogen atoms is perfectly symmetrical. Very few molecules are totally non-polar. The only way you get a completely non-polar covalent molecule is if you have two of the same atoms joined together. In most molecules, the bonding is not purely covalent. The reason for this is that the electrons in the bond are more strongly attracted to one atom than they are to another. So, for example, HCl, hydrogen chloride, the bonding electrons will be more attracted to the chlorine nucleus than the hydrogen. The reason for this is that the chlorine nucleus is larger, you've got more protons in the nucleus, and therefore has a greater pull or attraction to the bonding pair of electrons. The result of this is that the chlorine side of the molecule becomes slightly delta negative, whereas the hydrogen side of the molecule is slightly positive. And this is what makes the bond a polar covalent. I'm just going to draw this slightly larger so you can see it. So you have this delta negative end to the molecule. So you can see here more of the electrons are around the chlorine than they are around the hydrogen. Hydrogen is delta positive. You've come across this before when we were doing electrophilic additional reactions of the alkenes. We actually have an ability to measure this scale of attraction. We call it electronegativity. This is a very important definition. Electronegativity is the ability of an atom to attract the shared pair of electrons in a covalent bond. And it's on a comparative scale. The most electronegative element is fluorine. Everything else becomes more electronegative as it approaches fluorine. So the least electronegative would be one of the bottom of group 1. So anything as you get closer to fluorine, things become more electronegative. So the electronegativity will increase as we go across a period. The reason for this is that the proton number increases, the shielding remains roughly constant, and as you're adding an electron to the same principal quantum shell each time, the atomic radius actually slightly decreases. Down a group, the electronegativity decreases. The reason for this is that yes, you increase the proton number, but that is offset by the increase in shielding and also the increase in the atomic radius. So the distance between the nucleus and the bonding pair of electrons increases. So obviously fluorine, as it's very small for its period, it also has the highest number of protons for its period. Again, we're going to ignore the noble gases. Oxygen is next, and notice oxygen has a higher electronegativity than chlorine. In your redox notes, you'll see that oxygen can pull out positive oxidation numbers of chlorine. The reason it can do this is because it is more electronegative. Fluorine is the only one that can cause oxygen to have a positive oxidation number. And it does this because it is the only element which is more electronegative than oxygen. You are given this in a table form in your data booklets, but it's quite useful to know that fluorine, oxygen and nitrogen are all very electronegative. That's important later on when we come to look at hydrogen bonding. So if we return to the HCl molecule, you can see that the shared pair of electrons between the hydrogen and the chlorine is closer to the chlorine nucleus because the chlorine is more electronegative. So the positive charge, which is due to the protons, will lie somewhere between the hydrogen and the chlorine nucleus, probably closer to the chlorine nucleus because the hydrogen only has one proton. However, the negative charge is due to the electrons, and that will be a centre of the electron cloud. And as the electron cloud is pulled more towards the chlorine, it will be obviously more towards the chlorine. So polar covalent bonds are bonds where there is a difference in electronegativity between the two atoms. One side will have a slightly positive, we call it delta positive, and one will be delta negative. Now, this separation of charge is called a dipole, and we can calculate a dipole moment by looking at the amount of charge and the distance between the centres of charge. So the next page, we're going to have a look at some examples of ionic bonds with partial covalent character, polar covalent bonds, and then pure covalent bonds, 100% covalent. So an ionic bond could be something like francium fluoride, where you've got a positive ion and a negative ion. Ionic bonds with partially covalent compounds, partially covalent character. We'll come back to these later on when we study Born-Haber cycles. They're important there. Polar covalent bonds, well, we've come across HCl, but you could also have things like HF, which is a very polar covalent bond. We've also looked at pure covalent bonds, for example, fluorine or hydrogen or chlorine or so on. What you should see, and we're going to go on and look at on the next page, is that the bigger the difference in electronegativity, the more ionic in nature the bonding. And if there's no difference in the electronegativity, you get a pure covalent bond. So there's no difference here. And there's a large difference here. There. Okay, so you go, as you get a bigger difference in the electronegativities, you have a more ionic bond. So it is possible, yes, to have a purely covalent bond. The reason for this is if you have two of the same atoms, you're going to have no difference in the electronegativities, and the electron cloud will be completely symmetrical. On the other hand, it is not possible to have a purely ionic bond. Even something like francium fluoride, which is very big difference in electronegativities, is only about 98% ionic. There is always going to be a little bit of covalent character. And the reason for this, even though there's a big electronegativity difference between these two, it's not infinite, and therefore there will be a little bit of sharing. There's still some distortion of that electron cloud. So at one end of our spectrum, we have something like sodium chloride, which is highly ionic. At the other end of the spectrum, we have something like chlorine, which is a pure covalent bond. And somewhere along the line, we have something like hydrogen chloride, which is a polar covalent bond. At GCSE, you might have learnt to classify things as ionic or covalent. And we said that metals bonded with non-metals were called ionic, and two non-metals bonded together were covalent. However, things are not that easy. As we've already said, there is nothing which is 100% ionic, and there are actually very few compounds which are 100% covalent. All the other compounds exist on a continuum between ionic and covalent. We can still classify things as ionic and we can classify things as covalent, but you have to understand that bonding exists on a continuum between these two extremes. And the way we can work out whether a compound is ionic or covalent is to look at the difference in the electronegativities. And to do that, we need the Pauling electronegativity index, and this can be found in your datasheet. So the electronegativity difference gives us the percentage ionic character. Anything less than 0.5 we say is going to be covalent. Anything between 0.5 and 1.6, about here, we say is polar covalent, and above 2 we say the bonding is going to be ionic. The problems comes in this area, the area between 1.6 and 2. If there is a metal involved, then we say the bonding is ionic. If only non-metals are involved, the bonding is said to be polar covalent. And this explains why you can get aluminium bonding covalently and ionically. So this helps us to explain the bonding in the aluminium compounds. So aluminium has an electronegativity of 1.5, chlorine is 3 and oxygen is 3.5. Notice we don't take any account of the numbers here, we're just looking at the difference of the bond itself. So we've got a bond between an aluminium and a chlorine, and that bond has an electronegativity difference of 1.5. So therefore the bonding is polar covalent. Whereas the differences between aluminium and oxygen is 2.0, and therefore the bonding is ionic. So by knowing the electronegativity differences, I can work out whether the bonding is covalent or ionic. But the important thing to remember is that everything exists on this continuum between these two extremes.